Oh, yeah. Every time I know. I did. Also, love the leather jacket. I'm really I'm ready. You have defense.
I am going to start by passing back your exam. You may have seen your exam grade already. It was there is a 13-point curve that will not occur again. So that means you need to learn from your mistakes this time. because you're likely to see some of it again. But you need to be prepared for the rest of the semester to put in even more effort, or to figure out what you're doing wrong, which that may be what needs to be done, is we need to have a chat, you and me, and figure out what's going on. But the fact of the matter is, I did curve this exam by 13 points. That is, if I recall, 11 percentage points. So a whole letter grade. Okay. Abby Armstrong. I'll have it for you Wednesday. Michael Bivens. Anna Heath. Shakira Davis. Seth Dawson. Keegan Dortch. Peyton Ingman. JC Ortel. Samuel Fannin. Mac Fox. Presley Galloway. Joshua Gottsfunner. Peter Hoff. Krista Harper. Eamon Henderson. Gracie Hill. Madeline Hill. David. Maya. Kennedy. Adam. Braden. Emma. Jason. Jaden. Tyler. Williams. Lacey. Faith. Love. Micah. Casey. Julie. Jessica. Logan. Ashlyn. Jaden. Caleb. Claire. Okay. I will be posting the answer key today. Yes. On the left-hand side, where you go into the online classroom, if you look shortly thereafter, you'll find exams. And it should be under that. And I'll gladly discuss what you missed with you. And again, check the answer key because I'm not infallible. Okay, we're going to pick up where we left off on Wednesday of last week with acid-base strength and talking a bit more about acid-base strength. When we finished, we were talking about whether or not a reaction is likely to occur the direction that it is written. So let's look at a reaction and determine whether the reaction is likely to occur in the direction that it is written. Let's take an acid of H2CO3 and add that to a base of H2 for some reason that something is not working. H2PO4 minus to go to form HCO3 minus. Plus H3PO4. When I have this, the first thing I do is I determine who my acid is, who my conjugate acid is, who my base is, and who my conjugate base is. In this particular equation, I notice that H2CO3 is the conjugate of HCO3 minus. Looking at that, that means the H2CO3 is the acid because it has the more hydrogens, and the other one is the conjugate base. Now, if that's the acid, I would expect the other one to be the base. And looking at this, when I look at the other pair, the one that has the most hydrogens is H3PO4. So this is your conjugate acid. And the H2PO4 minus is your base. Now, last time when we spoke, I gave you a chart that you will receive on homework and you would receive on an exam. And looking at this, the first thing I do is I compare my acids of H3PO4 and H2CO3. And I find that H3PO4 is the stronger acid. I also compare my bases of HCO3 minus and H2PO4 minus. And what I find out is HCO3 minus is the stronger base. So this reaction is going to prefer the reverse direction. Because a reaction should always move from the stronger acid-base pair to the weaker acid-base pair. In other words, the other thing it means is if I add H2CO3 and H2PO4 minus together, you could expect no reaction because it's not going to move from a weaker acid-base pair to a stronger acid-base pair. Questions?
Is the reason that H3O3 minus is a stronger base, is that because it has less hydrogens in it?
There's a couple of different reasons. It isn't a matter of less hydrogens. It is more likely due to the fact that you can distribute that electron pair, that negative charge, over more atoms in the H2PO. Well, let's see. No, you can't either.
I guess like what I'm trying to know is like, is there like a rule?
Oh, it's because of the one rule of thumb is you can look at the oxidation state on the central atom. And PO4 still has a higher oxidation state than the carbon. The phosphorus has a higher oxidation state than the carbon. Okay. So we've been talking about, so what we've talked about in chapter 16 is the fact that acids can be described as strong acids, meaning they dissociate completely in water, or weak acids, meaning they only partially dissociate. The strength of an acid is really dependent upon how well that negative charge can be distributed over the entire molecule. Now, I gave you a couple of things that will help you to identify the degree to which that electron charge is distributed over the molecule. One occurs if you have a binary acid. In a binary acid, the bigger the anion, the stronger the acid, because again, it has a larger atom to distribute that negative charge. For a polyatomic ion, you can look at the central atom in the polyatomic ion, and the greater the oxidation state, the more likely it is to be a stronger acid. Now, if you want to get into the real reason, it's because typically those higher oxidation states also have lots more oxygens associated with them, where the electrons can be distributed over multiple oxygens. But the easiest way to tell is on an oxyacid is simply to look at the oxidation state of the central atom. The other thing we talked about is when we deal with an acid and a base, we using the Bronsted-Lowry definition of acids and bases, you can develop conjugate acid-base pairs. These are acids and bases that differ by a single hydrogen. And the last thing we talked about, which I picked up with today, is the fact that if you have a reaction of acid-base, conjugate acid-base pair, the reaction is always going to move in a direction so that it goes from stronger acid-base pair to the weaker acid-base pair. Now, I want to go back and talk about acid-base strength a little bit more. And we're going to specifically get into acid strength. And Ka, which is called the acid dissociation constant. It is the equilibrium constant for acid dissociation reactions. Now, we talked about hydrochloric acid, for example. Hydrochloric acid, aqueous, reacts with water, liquid. And because it is a strong acid, we have complete dissociation. So we show that it is a single-headed arrow. And that goes to form hydronium plus chloride. Now, I have looked up the equilibrium constant for this, and the Ka for this is 1 times 10 to the 6th. Because it is such a large dissociation constant, you would expect essentially all products in solution. Now, in reality, I had to go searching for that equilibrium constant. What you will find is that Ka's for strong acids are not frequently published in Ka tables. For the most part, all you're going to ever find when you look at a Ka table is Kas for weak acids. The Ka table in your textbook is table C1. This table occurs, I should have looked at the page, in appendix C1, I should say, on page A14, appendix 4, page 14. But it occurs before your answer keys to the book questions. So again, another way we can determine acid strength is a lot of times we can look at the equilibrium constant, the acid dissociation constant. If it has an acid dissociation constant listed in the table, then it's typically a weak acid. It's very rare that it's going to be a strong acid. Yes.
So, like, whenever we're doing our equilibrium constant thing, there's that table where it's like, if it's a negative exponent, it's leaning towards reactants, and it's positive products. Is it the same rule?
It's still the same rule.
So, like, this means it's a stronger acid on the product side, so it's leaning towards.
Well, it means that it's no. Oh, I'm sorry. With this, what it means with a large Ka, it means that you pretty much only have product. You do not have reactant. And it is not a strong acid on the reactant, on the product side. It's only a strong acid on the reactant side. Because the stronger the acid, the weaker the conjugate base. So you can expect that to be an extremely weak conjugate base and weak conjugate acids. Okay. So you can have monoprotic acids, which is what hydrochloric acid is. It's also what acetic acid is. When you have acetic acid and you react that with water, it's going to set up an equilibrium to have acetate as the conjugate base and hydronium as the conjugate acid. The equilibrium constant for acetic acid is a Ka of 1.8 times 10 to the negative 5. Again, that's what I was trying to describe a minute ago, is that the equilibrium so in this particular case, we would expect more reactant than product in solution because it has such a small Ka. And that equilibrium constant is easily found in an equilibrium, in a acid dissociation constant table. Now, you can have things like a diprotic acid. A diprotic acid would be, an example would be that of oxalic acid. When you take oxalic acid and add it to water, it dissociates in a stepwise fashion, meaning you are going to lose one hydrogen at a time. Oxalic acid has a value of 6.0 times 10 to the minus 2. So in other words, oxalic acid is not as weak of an acid as acetic acid. Oxalic acid, you're going to have pretty close to even amounts of reactants and products because you're getting close to that 1 mark. Now, the hydrogen oxalate ion it can dissociate in water to form oxalate ion and hydronium. The monoprotic, the hydrogen oxalate, has a value of 6.1 times 10 to the minus 5. What do you notice about the second deprotonation, as it is called? The Ka is smaller, which means that the second reaction is less likely to occur than the first deprotonation. We can also have triprotic acids, such as phosphoric acid. Phosphoric acid, just like oxalic acid, is going to dissociate in a stepwise fashion, meaning you're going to lose one hydrogen at a time. The phosphoric acid has a value of 7.5 times 10 to the minus 3. Now, when you take the dihydrogen phosphate and react that with water for, again, a single deprotonation, the diprotic form of phosphate has a Ka of 6.2 times 10 to the minus 8. But again, phosphoric acid is a triprotic acid, so technically you can have one more dissociation. To form PO43 minus and hydronium. And that will have a value of 4.2 times 10 to the minus 13. Once again, what you will notice is that for every deprotonation, the Ka associated with that deprotonation becomes smaller and smaller, meaning that for every deprotonation of a weak acid, it is less likely to occur. So basically, to summarize up to this point, the Ka can tell you to what degree a dissociation in water will occur. The larger the Ka, the greater the dissociation. Your strong acids have such large Kas that you'll rarely find them in the acid dissociation constant tables. But your weak acids, those you will find. The second key thing that has come out of this is that when you have multiple protons, multiple hydrogens that can dissociate from the acid dissociation constant gets increasingly smaller with every deprotonation, meaning that it is less likely to occur. Questions so far? We're going to come back to these dissociations in a little bit. But right now, we need to talk about what else is going on. If you look at these examples and many of the examples I've given you to date, what you would see, whether it's acetic acid, in water to make acetate, and hydronium, or whether it is ammonia in water to make ammonium and hydroxide, what you will notice is that water is frequently involved. The second thing you would notice if you do the conjugate acid-base pairs is that in the first reaction, the water is acting as a base, but in the second reaction, the water is acting as an acid. Water is amphoteric. Which means that it can act as an acid or a base. Well, if it can act as an acid or a base, that means in a pure water system, it can act as an acid and a base. To form hydronium and hydroxide. This is referred to as the auto ionization of water. Just like any reaction at equilibrium, we can develop, we have an equilibrium constant. The equilibrium constant for the autoionization of water is referred to as its Kw. Equilibrium constant for water, literally. And at 25 degrees Celsius, that equilibrium constant is equal to 1 times 10 to the negative 14. Just like with any equilibrium reaction, we can write an equilibrium expression. And that Kw would be equal to the hydronium concentration times the hydroxide concentration. And since we only include aqueuses and gases, it is over 1. So it's simply equal to the hydronium times the hydroxide.
why it's important. that it's okay.
Because you only include aqueuses and gases. Now, we can develop a expression from our reaction of H2O liquid. Two of those. I'm no longer going to write them separately. Dissociating to form H3O plus OH minus. If we think about our rice table, because we have a liquid, that does not have any impact on what's going on. We have 0 of our hydronium and 0 of our hydroxide when the reaction begins. The change, again, there's really no change in our water amount because it's a pure liquid. But we will gain X amount of hydronium and X amount of hydroxide. So that at equilibrium, we have X amount of hydronium and X amount of hydroxide. We can develop our Kw expression that is equal to the hydronium times the hydroxide. And if we're at 25 degrees Celsius, then we can substitute in the fact that 1 times 10 to the negative 14 is equal to the Kw. And at equilibrium, that's equal to X times X, or X squared. If we take the square root of both sides, then we get an X value of 1 times 10 to the minus 7. So, in a neutral solution of water, the hydronium concentration equals the hydroxide concentration, and both of those is equal to 1 times 10 to the minus 7. It's neutral because there's nothing else involved but the water. Any questions about the autoionization of water? Folks, this equation needs to be second nature. You will use it a lot. Why will you use it a lot? Well, I mentioned, though I did not illustrate, the fact that all of our reactions are taking place in water. So let's say I have hydrochloric acid and I react that with water to form hydronium and chloride. This is not the only reaction occurring. Not only do you have the dissociation of acid, but because it is in water, you have the autoionization of water occurring. This reaction, because you are dealing with an acid, is going to control the H3O plus concentration. But Kw equaling to hydronium times hydroxide is still going to apply and will determine the hydroxide concentration in solution. Now, admittedly, the greater this hydronium concentration, due to the dissociation of the acid, when you plug that into the Kw expression, it's going to greatly reduce the hydroxide concentration. So, this dissociation, since it controls the hydronium, that means you're going to have a lot of hydronium because you got an acid present. You plug that concentration of hydronium into this Kw expression, it's going to lower that hydroxide concentration. So when you have an acid present, you have very, very, very minuscule amounts of hydroxide from the water dissociation because it's not going to dissociate to any great extent. Questions? In an acidic environment, what we're going to find out is that the hydronium concentration is going to be greater than 1 times 10 to the minus 7. And the hydroxide concentration is going to be significantly less than 1 times 10 to the minus 7. Folks, we can make the same argument, but go with a base. If I take sodium hydroxide and I allow it to dissociate, it's going to form sodium ion and hydroxide ion. But folks, this is taking, and therefore my, I would expect this base to control the hydroxide concentration. but it is still in an aqueous solution. So what else is present? Water. So we still have two waters dissociating to form hydronium and hydroxide. We're still going to use Kw to determine, in this case, we'll use it to determine the hydronium. And for the exact same reasons, but reverse of what I described earlier, we're going to find out that in a basic solution, the hydroxide is going to be greater than 1 times 10 to the minus 7. And the hydronium is going to be less than 1 times 10 to the minus 7. The reason is because this hydroxide is going to control. It is going to be large. And if we put that large hydroxide into the Kw expression, it's going to give us a very small hydronium. We're going to be using all of this knowledge about the autoionization of water and the Kw expression when we talk on Wednesday and we get into the dissociation of strong acids and strong bases and figuring out their pH, which we've got to discuss, POH, which we've got to discuss, their hydronium concentration and their hydroxide concentration. We're moving into actually getting involved in these acid-base dissociation reactions. And then we'll get into titrations. I will see you on Wednesday. Huh? We do have lab tomorrow. Tomorrow we are doing KEQ lab.